Welcome to this video. We're going to be talking about financial and other applications of geometric and arithmetic sequences and series. This is aligned with Mathematics Analysis and Approaches Standard 1.4. So one of the most useful real-world applications of geometric sequences and series is compound interest. So let's look at an example of how this works. Suppose you had $1,500 invested in an account and it grows 5% interest every year. And let's say that's compounded daily. And you, on top of that, invest an additional $150 each month into your account. How much money will you have in 18 years? So we can use a geometric sequence and a series to actually figure this out. All right, let's draw the situation to get a better idea of what's going on. So you initially invest $1,500 into your account. That's what you start with. Now that money is going to grow by some rate. Then after that, you're going to add $150. Now your new balance is $1,500 grown by that rate plus $150. And then all of this is going to grow by some rate again. And then you're going to repeat the process by adding $150 the next month. And then all of this is your new money. It's going to grow by some rate again. And you'll add $150. This process will continue on and on as many months as you're adding $150. You can actually simplify this a little bit. If you distribute this r into the expression, it actually becomes 1500r cubed plus 150r squared plus 150r plus 150. And of course the values of r will grow as you grow in months. So it would approach n, where n is just how many months. This is the general idea of what's happening. But now we're going to explain it using a geometric series. Okay, let's talk about some formula craziness. I know this page looks a little overwhelming, but we're going to break it down piece by piece and it's going to make perfect sense. So we're going to start with 1500 here. That is your initial amount. And you're going to multiply it by this whole expression is really just your rate, r. And this represents 365 because it's compounded daily times how many years. You're investing for 18 years. So that's why you have to this power. So it's 1500 times the rate to that power. Now that's added to, and remember the 150 kept going on and on, that was just a geometric sequence, a geometric series. So we use the summation notation, and it's going to go to 18 times 12. Well, 18 is how many years, and then 12, there's 12 months in a year, so that's why you have 18 times 12, because that's how many months happen in 18 years. And then 150, this is the same rate, because it's growing by the same interest, compounded daily, that's why you see 365. And then this is going to be to the power of 30i. Now 30 because it's compounded daily, there's 30 days in a month, and then I because as we grow, you'll see the 150. The first one will be 30, and the next one will be 60, and then 90, so on and so on as you grow towards the total number of months. So let's figure out what this whole thing equals. Using what we know about geometric series, we can calculate this sum. So let's do a little simplification. Let's let r equal 1 plus our interest rate, 5%, divided by 365. So that'll give us daily. And then we can rewrite the expression from the previous slide in the following way. 1500 r to the 18 times 365 plus this whole summation. So we see here that this is going to be, well actually this whole thing right here is actually U1. And then our rate is this, R30. So let me write that. U1 is going to equal 150 R30, and the rate is going to equal R to the 30. So we remember our formula, which is U1 times 1 minus R to the n over 1 minus R, and that's where we get this big expression right here. And of course we just bring this down, plug in what we know, and we figure out that the value is 55,970 12 cents. So in other words, after 18 years of investing, starting with 1500, adding 150 every month with a 5% per year interest rate, this is how much money you would have after those 18 years. Okay, so not every question we're dealing with is going to be nearly that complicated as the previous example, but that illustrates the usefulness of a geometric series and sequence in a compound interest situation. But whenever you're solving these questions, here's what you need to look for. First off, read the question very carefully. You need to extract the following useful information. Determine the starting amount, U1. What is it that you're starting with in terms of money or in terms of amount of something? Determine the rate of increase, so that's your R, or decrease, depending if R is negative. Determine how often there is compounding, so this is in regards to money. And then determine how much time will pass. And that's important whenever you're talking about not t, value of n. How long will this process continue? Okay, let's try a practice example. The number of Facebook users at the end of 2008 was 145 million and growing at a rate of about 1.4% per week. If the rate of growth had remained constant, determine the number of users at the end of 2010. Okay, let's start with our starting amount. This is going to be 145 million. I'm just going to write 145 and keep in mind that's in terms of millions. My rate is going to be growing by 1.4%. So I'm going to write that as 1.014 because when you multiply that by a number, it's going to give you a number that's 1.4% bigger. And then let's figure out what is in the time that's going to take. There's compounding per week. So that means if we're going from 2010 to 2008, 2 years times 52, because there's 52 weeks a year, that gives us 104 weeks in total. So now we can put it all together to determine how many users there would be. So UN is going to equal my U1, 145, times my rate, 1.014, to the power of n minus 1. And remember, I'm just using the general formula for a geometric sequence, not a series, because we're not adding the users. We're just determining how many users there were. So that would be UN equals 145, 1.014 to the 104 minus 1 would be 103. If you plug this in a calculator, you get about 607 million users. That's it for this lesson. Now go ahead and try some practice on your own.